Alice and Bob live in tree forts which are far apart with no line of sight between them, and they need to communicate. So they decide to run a wire between the two houses. They pull the wire tight and attach a tin can to each end. Allowing them to send their voices faintly along the wire. However, there is a problem: noise. Whenever there is a high wind, it becomes impossible to hear the signal over the noise. They need a way to increase the energy level of the signal to separate it from the noise. This gives Bob an idea. They can simply pluck the wire, which is much easier to detect over the noise. But this leads to a new problem. How do they encode their messages as plucks? Well, since they want to play board games across a distance, they tackle the most common messages first. The outcome of 2 dice rolls. In this case, the messages they are sending can be thought of as a selection from a finite number of symbols. In this case, the 11 possible numbers, which we call a discrete source. At first, they decide to use the simplest method. They send the result as the number of plucks. So to send a 3, they send 3 plucks, 9 is 9 plucks, and 12 is 12 plucks. However, they soon realize that this takes much longer than it needs to. From practice, they find that their maximum pluck speed is 2 plucks per second. Any faster and they will get confused. So 2 plucks per second can be thought of as the rate or capacity for sending information in this way. And it turns out that the most common roll is a 7, so it takes 3.5 seconds to send the number 7. Alice then realizes they can do much better if they change their coding strategy. She realizes that the odds of each number being sent follows a simple pattern. There is 1 way to roll a 2, 2 ways to roll a 3, 3 ways to roll a 4, 4 ways to roll a 5, 5 ways to roll a 6, and 6 ways to roll a 7, the most common, and 5 ways to roll an 8, 4 ways for a 9, and so on, back to 1 way for a 12. And this is a graph showing the number of ways each result can occur, and the pattern is obvious. So now let's change the graph to number of plucks versus each symbol. She proceeds by mapping the most common number, 7, to the shortest signal, 1 pluck. She then proceeds to the next most probable number, and if there is a tie, she picks one at random. In this case, she selects 6 to be 2 plucks, and then 8 to be 3 plucks, and then back to 5 to be 4 plucks, and 9 is 5 plucks, and back and forth until we reach 12, which is assigned to 11 plucks. Now, the most common number, 7, can be sent in less than a second, a huge improvement. This simple change allows them to send more information in the same amount of time on average. In fact, this coding strategy is optimal for this simple example, in that it's impossible for you to come up with a shorter method of sending 2 dice rolls using identical plucks. However, after playing with the wire for some time, Bob hits on a new idea. How is it we should measure information in a way that applies to any communication system you can think of? Human, animal, or alien? Well, let's return to the late 19th century, where at the time we were focused, as we are today, on speed. And one goal to improve speed was to design a machine which allowed the operators to input letters, which we can think of as primary symbols, and have the machine automate the lower level signaling events, such as pulses of electricity, what we can call secondary symbols. And machines can be driven by some clock source, allowing it to generate a precise and rapid pulse stream, which presumably would run much faster than any human hand. And one great example of this was the Baudot multiplex system, and the design was put into service in 1874. And it built off the same conceptual ideas we've seen in the shutter telegraph. It consisted of 5 keys which could be played in any combination. Think of it as a chord. Each combination would represent a unique message. With 5 notes, each either on or off, you can play 2 to the power of 5 or 32 different chords. The code assigned the 32 different chords to each letter of the alphabet, with the leftover used for carriage returns, new line, and spaces. So the operator would literally play letters, and their machine would automatically output a pulse stream representing the letters.
Like this for letter T. Or like this for letter R. Or like this for letter B. So we have an output signal containing various combinations of DC impulses, a signal that accurately represents the message typed on the teletypewriter.
Behind the counter, the mechanical nerves of the system change words to holes on tape, and the holes on tape to electrical impulses speeding over the wires.
Notice at the lowest level, this system is exchanging either the presence or absence of electrical current in a sequence divided using a clock. So how fast can our internal clocks run? Well, the limiting speed was not the clock. Then and today, the speed of transmission was physically limited by the minimum spaces between these impulses, or the pulse rate. And this problem plagued engineers who were testing underground submarine cables using the existing Morse code system. And it's similar to an echo or a sustained note. If one sends dots too fast over a long undersea circuit, they will run together at the receiving end. Because the symbol we receive at the far end of the circuit will be a slightly longer, smoothed out rise and fall, not an exact replica. And sending pulses too fast results in intersymbol interference. This occurs, for example, when the longer flow of a current bleeds into the next time division and perhaps reverses a 0 to a 1. So even if we are automating the detection of these current levels, there is a fundamental limit to how far we can squeeze 2 pulses together. And this is the same problem Alice and Bob ran into with their string communication system, which we called the maximum pluck speed. If they plucked any faster than 2 plucks per second, they noticed they started to bleed together and they got confused. So this is called the symbol rate. Remember, a symbol can be broadly defined as the current state of some observable signal, which persists for a fixed period of time. Whether you are using fire, sound, electrical current, anything, a signaling event is simply a change from one state to another. So the symbol rate is the number of signaling events which can be squeezed together in 1 second. It also became clear that there was one other way to increase the capacity of a communication system. We can increase the number of different signaling events. For example, with Alice and Bob's string communication system, they soon found that varying the type of plucks allowed them to send their messages faster. For example, hard, medium versus soft plucks, or high pitch versus low pitch plucks by tightening the cable different amounts. And this was an idea implemented by Thomas Edison, which he applied to the Morse code system. And it was based on the idea that you could use weak and strong batteries to produce signals of different strengths. He also used 2 directions, as Gauss and Weber did, forward versus reverse current, and 2 intensities. So he had plus 3 volts, plus 1 volt, minus 1 volt, and minus 3 volt. 4 different current values which could be exchanged. It enabled Western Union to save money by greatly increasing the number of messages the company could send without building new lines. And this is known as the quadruplex telegraph, and it continued to be used into the 20th century. But again, as we expanded the number of different signaling events, we ran into another problem. For example, why not send 1,000 or 1,000,000 different voltage levels per pulse? Well, as you may expect, fine-grained differences lead to difficulties on the receiving end. And with electrical systems, the resolution of these differences is always limited by electrical noise. If we attach a probe to any electrical line and zoom in closely enough, we will always find minute undesired currents. And this is an unavoidable result of natural processes such as heat or geomagnetic storms and even latent effects of the Big Bang. So the differences between signaling events must be great enough that noise cannot randomly bump a signaling event from one type to another. Clearly now we can step back and begin to define the capacity of a communication system using these two very simple ideas. First, how many symbol transfers per second, which we called symbol rate, and today it's known simply as baud for Emile Baudot. And we can define this as n, where it's n symbol transfers per second. And number two, how many differences per symbol, which we can think of as the symbol space. How many symbols can we select from at each point? And we can call this S. And as we've seen before, these parameters can be thought of as a decision tree of possibilities. Because each symbol can be thought of as a decision where the number of branches depend on the number of differences. And after n symbols, we have a tree with s to the power of n leaves. And since each path through this tree can represent a message, we can think of the number of leaves as the size of the message space. And this is easy to visualize. The message space is simply the width of the base of one of these trees. And it defines the total number of possible messages one could send given a sequence of n symbols. For example, let's say Alice sends Bob a message which consists of 2 plucks, and they are using a hard versus soft pluck as their communication system. This means she has the ability to define 1 of 4 possible messages to Bob. And if instead they were using a system of hard versus medium versus soft plucks, then with 2 plucks, she has the ability to define 1 of 3 to the power of 2 equals 9 messages. And with 3 plucks, this jumps to 1 of 27 messages. Now, if instead Alice and Bob were exchanging written notes in class, which contain only 2 letters on a piece of paper, then a single note would contain 1 of 26 to the power of 2, or 676 possible messages. It's important to realize now that we no longer care about the meaning applied to these chains of differences, merely how many different messages are possible. The resulting sequences could represent numbers, names, feelings, music, or perhaps even some alien alphabet we could never understand. When we look at a communication system now, we can begin to think about its capacity as how many different things you could say, and we can then use the message space to define exactly how many differences are possible in any situation. And this simple yet elegant idea forms the basis for how information will be later defined. Alice and Bob have figured out how to transmit messages between their tree houses. At first they used flames at night and shutters during the day. Then they used a wire which they plucked in different ways. Eventually they electrified this wire to send electrical pulses, and we're now at work on an experimental wireless method. The problem is, in order to pay for their equipment, they needed money. So they decided to offer their service for a fee to others. And on the first day, Alice had 3 new customers who wanted to transmit messages to their friends over at Bob's treehouse. The first customer wanted to send a list of 10 coin flips. The second customer wanted to send a 6-letter word. And the third customer wanted to send a poker hand. The question now is, how much should she charge? Well, the price of a message should depend on how long it takes Alice to transmit it. But how could she measure the length of different types of messages using a common unit? To find out, let's play a game. Imagine you are Bob now, and you know Alice wants to send you these messages, but all you can do is get the answer to yes or no questions you've arranged. Alice will answer by sending a sequence of zeros or ones using some method of variation. Recall that all their methods of transmission involve the exchange of differences, so a 1 could be represented by an open flame, or an open shutter, or an electrical pulse. No matter how they are manifested, we can simply call them binary digits, because a binary digit can have only one of 2 values, 0 or 1. So let's say 0 represents a no, and 1 represents a yes. Your challenge now is to always ask the minimum number of questions in order to determine the exact message. First, let's consider the coin flips. For each symbol, the sender, Alice, can be thought of as selecting one of 2 different symbols, heads or tails. Now, how many questions do you need to ask to determine which she selected? 1 question, such as, is it heads, will suffice. For 10 flips, what is the minimum number of questions? Well, 10 flips times 1 question per flip equals 10 questions, or 10 binary digits to transmit this message. Next, let's consider the letters. For each symbol, the sender Alice can be thought of as selecting one of 26 different symbols. Let's start with the simplest message, which is 1 letter. How many questions are needed? Is it A? Is it B? Is it C? Is it D? And so on. But that is not the minimum number of questions. The best you could do is ask questions which eliminate half of the possibilities. For example, the middle of the alphabet is between M and N. So we could first ask, is it less than N? If we receive a 1, yes, we cut out half of the possibilities, which leaves 13 left. And since we can't split a letter in half, we divide the possible symbols into sets of 6 and 7 and ask, is it less than G? We receive a 1, which is yes, and now we are left with 6 possible letters. And we can split them in half and ask, is it less than D? We receive a 0, which is no, leaving us with 3 possible letters. And now we can pick a side and ask, is it D? We receive a 0, which is no, and finally we are left with 2 possibilities. We ask, is it E? We receive a no, and after 5 questions, we have correctly identified the symbol, F. Realize that we will never need to ask more than 5 questions. So the number of questions will be at least 4 and at most 5. And in general, 2 to the power of number of questions equals the number of possible messages, which we previously defined as the message space. So how can we calculate the exact average or expected number of questions given a message space of 26? We ask the reverse question. 2 to the power of something equals 26. And to answer these types of questions, we naturally use a logarithmic function base 2. Because log base 2 of 26 is the exponent 2 needs to be raised to give us 26, which is approximately 4.7. So on average, approximately 4.7 questions will be needed per letter at minimum. And since she wants to transmit a word with 6 letters, Bob can expect to ask at minimum 28.2 questions, which means Alice will need to send at most 29 binary digits. Finally, let's apply this formula to a new message, the poker hand. Well, for each symbol, the sender Alice can be thought of as selecting one of 52 different symbols. And in this case, the number of questions is the same as the number of times we need to split the deck and ask Alice which pile it is in, until we are left with one card, which we will find is usually 6 splits or questions, and sometimes 5. But we can save time and just use our equation. Log base 2 of 52 is approximately 5.7, since 2 to the power of 5.7 is approximately 52. So the minimum number of questions on average is 5.7 per card. A poker hand contains 5 cards, so to transmit a poker hand requires 28.5 questions on average. We are done. We now have our unit. It's based on the minimum number of questions to define the message, or the height of the decision tree. And since Alice transmits this information as binary digits, we can shorten this and call our unit the bit instead of binary digit. So we have 10 coin flips requires 10 bits, the 6-letter word requires 28.2 bits, and the poker hand requires 28.5 bits. Alice then decides to charge 1 penny per bit and begins collecting her fees. Now, this idea emerged in the 1920s. It was one of the more abstract problems that communication engineers were thinking about. Ralph Hartley was a prolific electronics researcher who built on the ideas of Harry Nyquist, both of whom worked at Bell Labs after World War I. And in 1928, Hartley published an important paper titled The Transmission of Information. And in it, he defines the word information using the symbol H as H equals n times the logarithm of s, where H is our information, n is the number of symbols, whether they're notes, letters, numbers, etc., and s is the number of different symbols available at each selection. And this can also be written as H equals the logarithm of s to the power of n. And Hartley writes, "What we have done then is to take as our practical measure of information the logarithm of the number of possible symbol sequences." So information is the logarithm of the message space. However, realize that throughout this lesson, we have been assuming that the symbol selection is random, a convenient simplification. However, we know that in reality, most communication, such as speech, isn't always random. It's a subtle mix of predictability and surprise. We do not roll dice when we write letters. And it is this predictability which can result in significant savings in the length of transmission. Because when we can predict things in advance, we shouldn't need to ask as many yes or no questions to define it. When we represent information, such as an image, digitally, it means we must slice it up into tiny chunks. This allows us to send an image as a sequence of color symbols. And these colors can be represented as unique numbers using some code. Consider the following challenge. Alice and Bob can transmit and receive messages in binary. They charge their customers 1 penny per bit to use their system. And a regular customer arrives who wants to send a message. And their messages are 1,000 symbols long. The meaning of the messages is completely unknown. Normally, this is sent with a standard 2-bit code, which results in charging for 2,000 bits. However, Alice and Bob already did some analysis on this customer before and determined that the probability of each symbol in the message is different. Can they use these known probabilities to compress the transmission and increase their profits? What's the optimal coding strategy? David Huffman famously provided the optimal strategy, which he published in 1952, and based on building a binary tree from the bottom up. To begin, we can list all symbols at the bottom, which we can call nodes. And then we find the two least probable nodes, in this case B and C, and merge them into one and add the probabilities together. Then we repeat with the next two least likely nodes and continue merging until you have a single node at the top. Finally, we label the edges in this tree with 0 or 1 in any order. Now the code for each letter is just the path from the top of the tree to the given letter. So for A, it's just one edge, or 1. This is now known as a Huffman coding, and for examples of the following type, you cannot beat it. Go ahead and try. For example, if you shorten the code for D to just 0, then a message 011 could perhaps mean D, A, or maybe just B. So for this to work, you'd need to introduce letter spaces which cancel out any savings during transmission. Now, how far does this compress the message compared to the original 2000 bits? Well, we just need to calculate the number of bits per letter on average. So we multiply the length of each code times the probability of occurrence and add them together, which results in an average length of 1.75 bits per symbol on average. That means with this Huffman coding, we can expect to compress the messages from 2000 bits to 1750 bits. And Claude Shannon was the first to claim that the limit of compression will always be the entropy of the message source. As the entropy or uncertainty of our source decreases due to known statistical structure, the ability to compress increases. While if the entropy increases due to unpredictability, our ability to compress decreases. If we want to compress beyond entropy, we must necessarily throw away information in our messages.